All right. Thank you. This is a little bit harder than I expected. I may need to abandon my backup solution. We'll see.
Welcome back to the second day of this evening. Please turn in your desk and we'll give those to students so that they can come to the banquet. If you're going to the banquet, there's going to be a trolley that'll take you there. It's 2 piers down on the water at the Maritime Museum. It takes about a 30-minute walk, so you can walk either direction. But if you don't want to walk, take the trolley over, maybe walk back. All that's up to you. We'll have the trolley circling between here and there, starting from 6 all the way to 10:30. We're going to kick things off over there at 6:15. So without further ado, it is my great pleasure to introduce Luiz André Barroso to you for our second keynote of PLDI 16. Luiz is a Google Fellow and VP of Engineering for the Geo platform at Google. This is the group responsible for collecting and curating maps and data that powers Google Search and Google Maps. Luiz's research at Google has focused on warehouse scale computing, energy proportionality, and storage system reliability. Prior to Google, Luiz was a member of the research staff at Digital Equipment Corp and Compaq, where he worked on modern multi-core architectures. Luiz is a ACM fellow and was program chair for ISCA and received his PhD in computer engineering from the University of Southern California. Today's presentation from Luiz is going to be about programming a warehouse scale computer. Please welcome Luiz.
Thank you. Good morning. I think this is only my second time attending PLDI, so thank you for inviting me. It's not a group of folks outside of the subset of you that work in my shop that I interact with very frequently, so I'm looking forward to spending some of the rest of the day also talking to some of you. So what I wanted to do today, since it may have occurred to you from the brief bio that Chandra just read, that I'm not really a programming languages specialist. So what I'll try to do is to try to tell you what some of the things that I know about in terms of building these computer system infrastructures that may affect programmers and the design and programming languages in particular. And in particular in the context of this thing, it's a bit of a mouthful that we began calling warehouse scale computing systems about sort of almost a decade or so ago, as a way to differentiate sort of your ordinary data center from these things that were emerging last decade from companies like ours and others that are building very large scale computer systems and beginning to treat the whole building as a computer as opposed to as a cluster or a network of workstations or a sort of a collection of computers. So I want to motivate my personal biases in this space by stating a few of my credos here. First, from my perspective, these are the most interesting devices in terms of computing devices in the world today. The top half of that represent things you wear, things you carry around. And the bottom half is the subject of my talk today. It's a representation of these warehouse scale computers. In fact, this is one of our data centers in Belgium. Now, I will betray my bias very quickly by saying that, you know, I love wearing these devices, but as a computer engineer and a software engineer, I'm actually more excited about the building than about the little wearable devices. And I'm going to tell you sort of briefly why. First, this thing sort of happened, right? Denard scaling, Moore's law, I would imagine these are all things that you're familiar with. It's one of these things that we can now predict with full confidence we are in real trouble because we are predicting the past, right? The effects of this are already over a decade old. And what this really means for this array of devices that I'm talking about is that we used to be able to come to keynotes and get people like me sort of showing up on stage and, you know, picking up a phone from their pockets and saying that this is more powerful than a Cray, blah, 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 right? And it was true, right? So it's a good prop. It's a good thing to use in a talk. I've done that many times before. And here, my Nexus P is about, depending on sort of what computing units you measure, is about the same firepower as, you know, Deep Blue, right? The first computer that beat a reigning world champion of chess back in the day. That's really remarkable to think about that, right? When you consider, and this is just to give you an idea, I think it's order of, you know, maybe 10 teraflops-ish or so, right, of computing. And in the case of the Nexus P, I'm not even talking about the GPUs on this thing, right? I'm just talking about the Qualcomm Snapdragon-ish sort of things, right? So here's the problem, right? If you sort of have internalized the consequences of this is not going to happen again, right? I'm about as old as Moore's law right now, almost exactly as old as Moore's law. And it looks like I have outlived it. And this thing has really profound consequences for us in the way how we think about where the center of gravity of really interesting, really big computing is going to happen. And my perhaps primary point in this talk, if you don't remember anything else, is that, you know, for anything that's really compute intensive, that really is going to be transformative from a computing standpoint, that's going to happen there. It's not going to happen on your phone. It's not going to happen on your device. And one of the key reasons for that is energy and this power. And the way to think about it is that as we try to squeeze as much energy, especially from untethered devices, and give it as much capability as possible, we really are looking at a situation where these devices will actually only be able to afford their energy budget to things that are necessary to do in the place where you are. Right? There will be no joules for anything else. They need to interact with you. They need to sense your environment. They're going to be using every piece of energy that they have available and every silicon it has available for that. And all of the stuff that really requires sort of computation of a larger scale is going to happen somewhere else. So I'm postulating this. You can question me in Q&A. But that's the premise for my whole talk. So I hope you believe some of it. Otherwise, the next half hour or so will be kind of boring. Hopefully not. So this is what the rest of the talk is going to be. I've hopefully told you why is it that I'm excited about this computer, these warehouse scale computers. And what I want to do is, in thinking about what to tell you about today, is try to put myself in your shoes and try to think about what are the kinds of things that you might want to know at a reasonably high level, in most cases, going a little bit deeper in some technical areas, only sparingly. But to try to give you sort of as much of a broad overview of what's interesting in this space in terms of what this computer looks like that might be useful to you as you think about programming and programming languages. So I'll start describing the computer. I'm going to talk a little bit about programming challenges, and then I'm going to talk about my favorite sort of new emerging sort of application area that I'm quite excited about, and we'll go forward. So let's start with the storage hierarchy, right? From a programmer, if you look at the storage that's available to you, primarily you have DRAM and flash, right? Let's forget sort of on-chip caches, things that are hardware managed for you. And this is kind of vaguely what it looks like, and it will vary from one data center to the next. You're running your program on a particular CPU and how long it takes for you to read 4 kilobytes of data. From a local machine, DRAM and flash. From a machine that's in the same enclosure, right, has some degree of proximity, and proximity in this case means much higher bandwidth. So you can assume that these racks or these enclosures have much higher internal connectivity than I have. And for this example, I'm assuming something in the order of sort of 40 gigabits per second. I'm also making assumptions in these examples that the storage and compute are all deployed together, right? You have servers with some DRAM and with some flash, and you just replicate that. And when you do that, you can't give all the bandwidth to storage, right? You need to have some bandwidth for computing. And for these sort of cartoonish examples, I'm just telling you this, I gave half of the bandwidth to storage. The other half of the bandwidth can be used for other things that are not storage. And this is sort of what the situation looks like. The first thing that jumps out is the big cliff on DRAM, right? Clearly connectivity, DRAM is fast enough, connectivity is slow enough that as you go to remote DRAM, the latency penalty is quite high. In flash, it's kind of interesting, right? It's not negligible, the differences, but the difference between accessing local flash and remote flash begins to be actually manageable, right? And I'm talking about, in some cases here, best case scenarios for sort of next generation software and maybe PCIe connected flash, so not your standard sort of SSD sort of drive you might have on your Mac Pro. Let's jump to bandwidth. Now, bandwidth is more interesting, right? A high-end PCIe connected flash device is anywhere between 5 and maybe the very top can go to 10 gigabytes per second or so, right? Whereas DRAM, it actually varies quite a bit, but 40 gigabytes per second is something that's actually rather achievable in today's systems, especially if you're looking at dual socket machines which cheat by having sort of many DRAM channels. And the thing that jumps out on that is what happens when you go from local to things that are outside of your local enclosure. Right? The quality of connectivity you have today, even with these relatively high-end assumptions for networking, make it such that from a bandwidth standpoint, remote flash and remote DRAM kind of look about the same, right? Which is interesting. And one obviously is much more expensive than the other, so you're going to have much more flash than you have DRAM on your system. So that's sort of an interesting aspect of this computer as well. So the implications of that, I mean, there are many, but the ones that I'll highlight is that, by and large, if you actually are doing sort of remote storage operations, almost always you pick remote flash over remote DRAM. I mean, the cases where you pick remote DRAM are the cases where your bandwidth needs are so small, or perhaps you're making accesses that are so small in terms of the size, right? Something that's 4 kilobytes or less, that perhaps, you know, some of the latency aspects of it begin to be sort of interesting. So that's something to take note of. The other one is that there's an opportunity on the flash space for us to begin imagining a world where flash is not something that belongs to a machine. It's something that belongs to a building. Flash is just about fast enough, but not too fast. Its speed begins to match the speed of maybe the highest end data center level networking we begin to see on the horizon, especially if you move on to next generation 100 gigabit per second, like sort of interconnects. You can begin to imagine a world where you don't need to worry about flash locality quite as much. A flash in your local machine, or a flash certainly in your rack, and maybe at some point anywhere in the data center, from a programmer standpoint, will be sort of, you know, have homogeneous performance. And that's fantastic, right? Because it simplifies programming of these things a lot, gives you the opportunity to have more resiliency by distributing data. There's a lot of good side effects of things like that. So let's move on. Well, actually, before we do, you may have noticed I didn't mention disk drives. Well, there's great news about disk drives. From a performance standpoint, they're so incredibly slow. They already are where I think flash is going to be soon, right? It doesn't matter, right? It absolutely doesn't matter for you to put your disk next to your CPU or your disk in the next building over, because their bandwidth for anything than sort of super well-behaved streaming workloads is ridiculously low, right? Is, you know, maybe if you have to seek at all, you are in the few tens of megabytes per second. The latency remains, if you have to do a seek at all, in the order of 10 milliseconds or so. So it doesn't matter, right? Now, disks are absolutely not going away, right? So they are just going to be very easy to program because they can just be sort of deployed in a rather arbitrary way and be shared actually quite finely across all of the systems in a given warehouse scale computer. So that's good news, I suppose. So let's talk about the computing elements itself. I just talked about storage. Now, in the computing side of things, there's a lot of interesting things happening. One of them is that it's getting actually harder to get predictable performance out of the computing elements we have today. And just focus on CPUs, you might have noticed how much more variability that is today in the CPUs that are available to us. And I'm going to mention, and it's variable in a lot of dimensions. I'm going to mention just two of them. First is this thing you call turbo mode in the case of Intel. Excuse me. But the idea is the following. We cheat on these chips today, right? We put so much silicon in there that if we actually light up everything, the chip melts, right? So if you have a multi-core CPU with, say, sort of 10 CPUs or so, in order to always be as close as possible to the thermal envelope of that package, you allow that CPU to run every core at the same time if you have workloads for all of them, but not at the highest possible frequency bin, because if you did so, you would go over that envelope. Now, if your program only uses a small subset of those CPUs, you can allow those CPUs to run at higher frequencies, right? Which is great if you think about it, because it really is exposing the physical limit of that system to you and allowing you to take advantage of that. From a programmer, is a bit of a bummer, right? Because, you know, old speed up Amdahl's law over there tells us, you know, how difficult it is to parallelize things to begin with. And you're familiar with the F's and the N's there being the fraction of computation that can actually be parallelized, and N being maybe sort of the number of elements or the factor by which you are speeding up sort of that fraction of computation. Now, what happens now is that when you go for, say, a serial version of a program to a parallel version of a program now, you went from using one CPU at a high frequency bin to using lots of CPUs that can't all run at the highest frequency bin, which is kind of a bummer, right? Because it hits sort of Amdahl's law twice, right? So, so this article from Uri Vernon and others, it was published at the IEEE Computer Architecture Letters, does actually a really nice descriptors of the problem, not just in the simplified way that I'm mentioning here that's more performance related, but also in terms of of analyzing the energy and the energy efficiency sort of artifacts of that. And what you see is that you added a new component there that tries to capture the fact that if you run n CPUs, you actually have a performance penalty by virtue of the fact that you can't run them as fast as running an n number that's smaller than that. And in that paper, for example, they actually did real studies on some of the sort of modern Intel server class CPUs. And those penalties are actually quite significant. So it's kind of a bummer, right? Because it's hard enough to beat Amdahl's law. And now you have to beat Amdahl's law. And you still have to worry about the fact that once you did a great job parallelizing things, you're still going to be hit with an extra penalty. Well, you're going to have to live with that. But you have to account for that when you're looking at parallelizing programs. The other part that's very interesting that hits us a lot at Google these days is that some of these CPUs have become so good and so aggressive at entering sort of deep power modes that and the delay that is incurred in actually getting out of those deeper power modes begin to actually be a problem in terms of performance idiosyncrasies. And this is one of the ones that I mentioned today. You can have a situation where you have a busy machine, a busy server, that you send requests to it, and the responds to you at 150 microseconds, which is sort of okay. And then you send that request to a server that's actually idle. And the response time is much higher, right? And you say, well, that shouldn't really happen, should it? And what happened was that very clever power governor on that CPU in the idle server was very aggressive, realizing that this CPU is mostly idle and shoving a bunch of those CPUs to very deep power states for which it takes a long time for them to come back from. So that's another kind of performance idiosyncrasy you have to be aware of. I mean, in some cases, we begin to have the ability of tweak these hardware mechanisms to change how aggressive they might be, for example, or maybe selectively enable and disable them for some subsets, of course, for which you need more responsiveness. One way or the other, these are effects that we actually see every day that are actually meaningful to the performance of our workloads. And if you go back 4 or 5 years ago, they weren't there. So one last computing complication I'll give you, I think it's potentially more an opportunity than a complication, but it's the fact that we live today in the warehouse scale computing world, in the world of microseconds. You probably noticed I may have said milliseconds once in this talk today, and I probably said microseconds 20 times. Right? And the reason is that warehouse scale computer is a microsecond machine. It's not a millisecond machine. The internet is a millisecond machine. Disk drives are millisecond machines. The data center networks on this thing are microsecond machines, right? If you imagine, sort of do a rough calculation for just speed of light and what it takes to sort of send photons, if you will, or bits from one end of the data center to the other, best case scenario is order of a microsecond or so. In reality, high-speed networks today actually get somewhat close to that, right? Single-digit microseconds for some of these HPC class networks. So that's interesting. Flash devices. 80 microseconds, there's some that are coming now to 50 microseconds. There's new non-volatile memory technologies coming even below that. Another microsecond device of interest. Accelerators, talking to a GPU that's on the other side of a PCIe bus. If you're going to cross a PCIe bus, you're going to burn a microsecond. Right? So it's not a nanosecond system. It's not a microsecond system. It's not a millisecond system. The problem is that we don't have a good way to program microsecond level things. We just overlook that, right? We're great at nanoseconds. The microarchitects took care of that. Things that are at the nanosecond level, the hardware takes care of it. That's prefetching, out-of-order execution, speculative execution, you name it, right? And somehow we do pretty good at keeping computer CPUs busy at the nanosecond level. And the programmer actually doesn't have to be bothered by that. You issue a load, things happen in the background, the value of that load shows up in the register later on today. The abstraction that's shown to you as a programmer is a fairly simple one. For millisecond level things, operating systems are good enough, right? Because milliseconds are so slow, and context switches are slow, but not that slow, right? The order of, you know, a handful of microseconds for a context switch. So millisecond programming is easy, right? Because you can block, the operating system takes care of it, brings it back, and you continue to have sort of efficient computing in that case. For microseconds, we are in this sort of funny gap that the hardware doesn't save you and the software is too slow. So if you try to actually create programs that take advantage of these new devices, data center networks, non-volatile flash devices, accelerators that are microsecond level devices, you have to work really darn hard to actually get the microsecond level performance. And that's something we need to solve, both from a programming standpoint as well as from a hardware standpoint. I actually believe there are hardware mechanisms that are missing that could help you there. And you know, my great example from my colleague Mike Marty is sort of this sort of quick analysis he did a long time ago of how do you destroy a low latency fabric, a low latency data center network, right? That's a network, you know, think of sort of an InfiniBand of a few years ago that you can do an RDMA in sort of 2 microseconds, right? So purely sort of hardware wire latency crossing one switch and things like that, right? Now, you begin to actually try to program this thing and make it useful for a programmer to use that because a low-level RDMA operation is actually not very usable. By saying, you know, making it two-sided, make really sort of a messaging protocol. And then, you know, you actually have to run something on behalf of a server, so you have to do a thread switch. And perhaps you can't be polling all the time, so you need to introduce interrupts. And then finally, you have to have a remote procedure call system or some sort of messaging library that's amenable and easy for programmers to use. And you quickly destroy your 2 microsecond network, and you are left with 80 microseconds or so. And you know, we've worked very hard to actually do much better than that in some of our internal high-speed messaging libraries. But boy, we had to work hard for it. Right? And that's a problem that's actually yet to be solved. We basically have overlooked this. And I expect that this is not going to be, we won't be able to afford overlooking at the time because all the exciting devices that are ahead of us, high-speed fabrics, next generation volatile, non-volatile storage, accelerators, they all are going to run in microseconds. If we don't solve that, we're going to have huge inefficiencies or very low program productivity in sort of building efficient systems on these warehouse scale computers. Switching gears to what's been happening, maybe most importantly for the last 5 years or so. Now, I'll take a short digression and mention that for a long time, I'm probably to blame for Google bad-mouthing any kind of specialized computing acceleration technology that's been out there. Right? And I've been right for a very long time until I was wrong. And there's many, many reasons for that. But what you see today is that's an increasing emphasis on non-general purpose computing and things of the kinds of, you know, GPUs and FPGAs and even sort of ASICs beginning to be considered in the data center. And that, you know, full disclosure, if you actually look at this book we wrote about data center computing, I openly badmouthed this whole idea of specialized computing in that book, in the edition that's not too far into the past. Right? So you can call me a flip-flopper if you're a politician, or perhaps someone who changed his mind in light of data. But you know, what happened that caused this to take place? There are basically 2 things. First, deep learning. And I guess I should disclose right now, I'm contractually obligated to talk about machine learning and big data on every keynote. Right? So check that box right now. So deep learning is suddenly fantastic because we know how to scale it. We actually have reasonably efficient computing engines to do that. And we keep finding it to be much less than sort of the niche application we thought it might be, you know, 10 years ago, to something that we keep finding just new ways to actually improve different areas of computing. So it went from being something that I'm never going to build specialized hardware for it because there's only these sort of, you know, niche use cases, to something that's beginning to be very, very widely applicable. The other reason is, you saw that before, right? That's hit general purpose computing particularly hard, and specialized computing cheat, right? because they are able to design systems that can take advantage of characteristics of the workload that a general purpose CPU is basically not allowed to do. Now, the final nail in my coffin in terms of turning around from being a skeptic, if you will, of specialized computing is the system we announced at Google I/O just about a month ago. So we at Google a few years ago realized that this deep learning thing actually was pretty big. And if there was a way to hardware accelerate that, we couldn't afford not to do it. So I started a program to build computing accelerators for deep learning in particular, machine learning in general, but deep learning in particular. And at I/O, we presented some, we unveiled, I think, for the first time, the fact that we have this ASIC that is, in many ways, you can measure it, order of 10 times more efficient than competing solutions for running deep learning applications. That's been running at Google for over a year now. It's been actually quite successful. And it's a proof point that these kinds of specialized computing techniques finally actually are seeing the light of day. Now, this is exciting in a lot of ways. One of them is that it can do things that people thought would take us a long time to do. And this is a demonstration of the power of this technology. And you may have heard from a few months ago that there was this challenge with a champion of the game of Go, in which this computer that was using this new ASIC actually was surprised surprised many of us at Google, actually, too, in being able to actually do quite well in that. But aside from this demonstration of the power of this kind of technology, the combination of techniques and hardware acceleration, this technology is useful in a lot of other ways. I mean, there's an immense array of products at Google that today cannot live without machine learning, and in many cases, deep learning and the deep neural nets in particular. This is sort of a eye chart for you to tell you sort of some of the places where this is actually, where you wouldn't guess. Our data center use machine learning to more effectively deploy cooling to different parts of the data center, right? It's amazing how much more applicable these kinds of technologies are than we envisioned. Chandra mentioned for the last nearly a year right now, I actually have been leading a team in Google, in the geo part of Google that powers Google Maps and things like that. And that team is one of the teams that's pioneered the use of this technology at Google, deep learning in particular, for understanding the world through images. And I'll give you some of the examples of the power of this that's quite remarkable. So these are storefronts, street signs, and a parking sign. And computers these days, using deep learning techniques, are actually better than human beings at transcribing these kinds of information, which is in itself quite remarkable if you think about it. But that's not the part that I think is more exciting. The part that's more exciting is that it's just not just being great at OCR. It's being great of actually understanding better what matters. So in that first case, breakfast, lunch, and dinner is actually not that important. The important thing there is that there's a place called Tommy's Cafe there. That's the relevant information. All this other information about the street sign, Setor Campinas, and the zip code down there is actually not useful for this particular work. What you want to know is the name of the street. And in particular, for parking signs, a raw transcription of that's not that useful, but something that's structured in a way that we can use to then help Google Map users know that they can park here or not park there is indeed much more useful. Another part that's actually interesting is using also this technology to understand things like abbreviations. This is much harder to show on this chart. But what you're seeing there basically is the fact that you can not just understand structure, but you understand enough of what a street sign is like in a particular country that you can expand things like abbreviations. This is my home country, Brazil. And street signs, and AV is an abbreviation for avenue. And you see how it's actually offset on top, right? And the system not only does OCR, but it understands that that is actually part of the street name, understand that this is Brazil, and therefore AV is very likely Avenida, and transcribes to our databases in the correct manner. Right? This is you know, it's a bit subtle, but it's incredibly clever to be able to do that and to be able to do the machine. And you can imagine the efficiency of mapping the world when you have this kind of technology. A street view car drives by, and you just learn all of these things about the world that can generate a very rich map, can give our customers sort of really interesting navigation experiences. So part of my skepticism about specialized computing had a lot to do with programmer productivity, right? My argument with some of my friends at Google against specialized computing systems as well, yes, it may actually be in some cases more compute efficient to do that. But if you're gonna slow down a software engineer, you're gonna lose, right? A software engineer is the most valuable and scarce resource in this world we are in today, right? You're not gonna take a trade-off that's gonna be around, I'm gonna speed up my system by 2 times, I'm gonna slow down productivity of my software team by a factor of 2. You are not gonna pick that, right? So what are we doing to make these more specialized computing systems more amenable to programmers? I'll give you just 2 examples. First, to plug some of the work for Robert Hunt and his team at Google, who have just released an open GPU compiler. This is a paper at this year's CGO. I will welcome you to take a look at. It's quite remarkable to be able to do such a thing. It's a system that actually, from a performance standpoint, is comparable to NVIDIA's compiler in terms of performance, but has the advantage of actually opening innovation in this area for, you know, for yourselves and for a very large community that can improve the quality of our programs and the productivity of engineers running against GPUs in particular. The other part, you may be familiar with that, is this set of libraries or programming system that Google open sourced a little while ago, maybe over 6 months or so ago, I forget, called TensorFlow. This is more specific to building machine learning applications. It's specifically tailored for deep learning. And it's very successful. It's probably one of the hottest things on GitHub these days in terms of forks. And part of the reason for that is that it allows you to, well, I'll get to that. It's a high enough level representation of these kinds of workloads, but not too high that it allows automated systems to actually do something with that. And do something meaning sort of optimizing it and actually retargeting to different kinds of computing devices. So at a very high level, what the model is basically a computational data flow graph in which sort of these nodes and operations are flowing through. The things that are going between nodes is data, and that's called tensors, therefore a TensorFlow. And these are n-dimensional arrays. There's some state involved with it as well. The system's clever enough, actually, to be able to know how to partition some of these things and automatically insert communication primitives so that if you actually have some of the computation running on the CPU and the GPU, the back end of the system will be able to actually do that for you. And this has been quite useful in terms of increasing the productivity of our programmers developing machine learning techniques with the safety net of knowing that if they build that, they can run it on a CPU, they can run it on a GPU, they can run it on a Nexus phone. In fact, I think I have a slide for that. And they can run it on our new ASICs, right, for all of that. And the underlying runtime infrastructure takes care of that. It's quite remarkable. Let me now switch gears a little bit and talk about, to finish my talk, some of the things that I think are, in my view, a very exciting new programming challenge. And here is where I check my second box. You might expect, right, given the buzz, that I want to talk about big data. And I'm not. First, because I have to confess to you, please don't tell anyone about this, but at Google we have a secret internal word for big data. We call it data. So I think it's fantastic. I'm not personally terribly excited about that, in part because it's too vague of a term for me to understand what it means. Now, there's a part of that problem that I'm interested in, and here's the motivation for it. Today, we interact with our computers basically using this device, right? It looks a bit different, right? It's got sort of a touch screen in some cases and all that, but it's by and large, that's what we do. And we're moving to a world where, you know, we're going to begin to actually have much more immersive experiences in which we're going to be sensing our environment at a much higher bandwidth. And we will expect internet services to actually provide, you know, different experiences in terms of interacting with the real world, enhanced by information from massive computers that understand where you are and what you're doing and what are the details about the real world. And for those experiences to actually be truly magical, there's a degree of responsiveness that is nearly impossible to do today with the networks and the devices we have. And I'm really interested in that because I really would like to see the final vision of these systems. And there are many incarnations of this kind of technologies, but you know, annotated reality sort of experience is one that I find particularly compelling. Now, the characteristics of the systems from a very high level is that, you know, especially if it's something that's going to give you visual information, the lag has to be incredibly small. So the responsiveness of these systems have to be in the, you know, few tens of milliseconds, in some cases less. But at the same time, they're often dealing with a tremendous amount of data. Not just the data that your sensors are sending to the computing engines to process, but also all the data and the computing that has to happen in the back end to give you that kind of experience as well, right? So we called it a while ago, in a couple of papers we wrote, these kinds of services, online data-intensive services. The hook into big data here is that it is sort of a big data problem, but it's a twist on the big data problem. It's a big data problem that has to actually respond in a small number of milliseconds or tens of milliseconds. And that is fun, right? Because big data problems that are big analytics problems are going to change the world. They're going to be fantastic. There are a bunch of things that are going to be solved by them. From a challenge to a computer scientist, it's actually a slightly easier problem because you have a bit of luxury of time to do some of these things. And responsiveness in very large-scale computing systems is a very, very hard thing to achieve, and we're finding that more and more. And I'm going to tell you a little bit why. Imagine you create a web service that's based on one server, and it's running very well, right? 99% of the time, it'll give you a great response time, sort of within 100 milliseconds or so. And 1% of the time, there's some kind of hiccup, right? Maybe the CPU went into a low power state, for example, and you get 1 second, which is sort of not acceptable from a response time latency. Well, it's an okay system. It's not, it's not an outstanding system, but it's pretty good. 99% of the time, you have pretty good experience with it. Now, what happens if you're lucky and your service now is actually quite popular? You need to scale it up, right? Assume now that you have 100 servers instead of one server. And imagine that in this model, your computation actually has to touch all of these servers to be able to accomplish the task at hand. The case in many of these big data, little time sort of applications. Search is the quintessential sort of example of that, right? So what happens there is that simply by taking that same server and replicating it 100 times, now, instead of having 1% of your queries being slow, 2/3 of your queries are slow. It's kind of a bummer, right? Because the system was working just fine. And all you did is you added a few more, and you end up with a slower system. Now, what have we been doing, sort of, and forgive the cartoonishness of this example, but what have we been doing in computer science as a whole to address this problem has been basically do things like, okay, 0.99 is not good enough, right? I'm going to do 0.999. And now things got a little bit better, right? Only 10% of your queries are slow. It's not great, right? Got better. Now, the issue is that getting from 0.99 to 0.999 is really hard. And it doesn't solve the problem. Because if you're still getting your service to be popular, now you don't have 100 servers, you have 2,000 servers, and you're back in the doghouse, right? The majority of your queries are slow. So the thing that I want to point out here is the following. If you want to have large-scale services that really are responsive, if you really want to achieve the promise of these big data, little time kind of systems, we need to begin create new kinds of techniques to deal with this problem. And here's where the analogy with fault-tolerant computing sort of comes handy. You know, back in the 1800s, 1900s, people built machines that didn't fail by using the machine, figuring out which components broke more, making that component bigger, thicker, right, more reliable, and building another machine, right? And that worked for a while. As machines began more complicated, airplanes in particular, for example, clearly that became a losing proposition, and redundancy had to come to play, and fault-tolerant techniques had to come into play. Now, what is fault tolerance at the essence? Fault tolerance is this magic that takes a bag of things that are unreliable and creates a system that is reliable, right? And that has enabled amazing things, right, in our world, in computing in particular. And I'm arguing we need an analog for that, for computing if we want to have responsiveness. It's a losing proposition to assume in systems that continue to scale that you'll be able to deal with these latency problems as you scale by whack-a-moling the next performance idiosyncrasy your system have. You need to have more principled solutions to these problems that will create a whole that's responsive, even if its subcomponents themselves are not. And Jeff Dean and I wrote an article outlining this basically as a challenge to the computer science community, because right now we know one great solution to that problem, and we are pretty sure there are others. But the one that we have and that we use at Google is on storage systems. And you can imagine how this works. Storage systems have the benefit that we already have replicated data because we need it for fault tolerance itself, right? So imagine you have a client and two servers that actually have the same copy of the data. Now, you can send a request to the first server, and you wait for a little while, and say you wait for the 95th percentile of what you expect the latency for that request to be. And if after that you haven't received a response from request A, you fire up the request A to the backup server. Now, pretty straightforward, right? Amazing how this cuts the tail latency of reads in the storage system. And at the same time, because in this particular case, you only fire up a backup request after waiting for the 95th percentile, you actually bound the extra load on the system by as much as sort of 5%, right? Which is pretty nice. Now, this system can get a little bit better if you are more agile at communicating in your system, and this by way of sending cancellation messages. Same situation again, you send a request to server 1, and then you just wait a little bit to bias the systems a bit, but nowhere near the 95th percentile, and you send a request to server 2. Now, assume server 1 actually schedules to serve that request first. As soon as it does that, it sends a cancellation message from one server to the other, which is another version of that same technique. It's amazing how these relatively simple things can take care of all sorts of performance problems, right? The server A could have been slow because of power issues. It could have been garbage collection. It could have been, you name it, right? The solution is actually irrespective of the actual problem. You don't have to go and solve any one specific issue. The system itself is robust to a wide array of different kinds of performance idiosyncrasies. And I went to sleep. Thank you. Ha! Just in time. Oh boy, I did exactly 45 minutes. So I wanted to leave a little bit of time to chat about some of the things we talk about here today. I mean, this is my sort of final pitch. I think this is an exciting time because, 10 years ago, perhaps, only people that wore a Google or an Amazon or a Microsoft badge sort of had access to this kind of computing power, and at the same time, access to these kinds of problems, right? And now, we have public clouds beginning to be sort of more popular across a wide array of vendors, which makes it more easy for us to engage a much broader community of people to solve some of these really hard problems. And the ease of programmability, I'll emphasize it one more time. This is not just a big machine, it's a really complicated machine. And programming productivity in the end is what wins in this game, right? And it doesn't matter if these machines are incredibly efficient and incredibly fast. We need to figure out a way to make programmers minimum amount of time sort of create great things on them. I'll thank you for your attention. I'll be happy to talk about these or any other things you might be interested in this general topic. Thank you. I will finish just very briefly by thanking some of the many colleagues at Google who either worked on or gave me some suggestions of what might be interesting to talk to you guys about.
Please come up to the mic and ask your questions.
Hey, you European man.
At least I pretend to be one. Jim Laris, EFL. So, very nice talk. Thank you very much. I have a question for you, though. The one programming model you mentioned in there was data flow in the TensorFlow. So, are there other programming models, asynchronous programming, you name it, that you think are necessary for this world that you outlined with latencies and failures and
Yeah, absolutely so, right? I mean, if you read some of the literature on TensorFlow, and if you use it a little bit, I think two things will hit you. One of them is you realize quickly that it's actually reasonably widely applicable, right, to things that are not necessarily subsets of, deep sort of net programming models. But it is restricted, right? It is actually reasonably domain specific. I am absolutely sure that there's space for many sort of other such things. The key is TensorFlow, and to some extent the specialized hardware we built, benefited from something that doesn't happen very often, which is a reasonably specialized kind of computation going gangbusters, right? Becoming so widely applicable that even though it's a relatively restrictive programming system, because these kinds of applications are becoming so widely applicable, it makes sense, right? I can't imagine a world where programmers will need to know 18 of such things, right? So I don't know what the next one is, but I venture to say that I'm pretty sure there are others out there. They may not be as big of a fit as a combination of the hardware acceleration and the relative scope, if you will, of the programming model being used. But I'm sure there are.
But what do Google programmers do now to program the systems that you've described?
Oh, a very good question. So there's a number of internal sort of infrastructure systems that we're increasingly sort of making it available through cloud offerings, right? On the responsiveness side of things, there's nothing that we actually have externally available right now, right? But ideally, you want to be able to build a system that, imagine it'll be sort of the MapReduce for online systems, right? It's a system that with the, you have a task to be done, and you know what the data is. You describe the computation. Maybe you give it some hints about what's the latency profile you want or the degree of redundancy you need, and the system automatically builds, right, a fail-tolerant system for you. I think that system is that kind of thing, and my best analogy is a poor one, sort of a MapReduce for online, for the big data, little time thing. I think that's a huge opportunity for all of us to seize on.
Hi, Ben Zorn from Microsoft. So I've really enjoyed your talk, and it came to mind a paper from Google called The Technical Debt of Machine Learning, where they actually talk about the challenges that machine learning brings to incorporating it into a programming, a bigger system. Do you have comments about that?
I confess I don't know exactly what they mean by that. Is it the difficulty of inserting a learned algorithm into sort of an existing piece of infrastructure? Is that what they mean?
Yeah, some of the perspectives were based on the issue of compositionality. So you have a piece a model, and then you want to update it, or you want to have version it. You want to incorporate a sub recognition within that. So it brings new challenges because these things are not pieces of they're not code in this traditional sense.
Yeah. Oh, I don't know that I can speak very intelligently about this. I know some of the problems we have in maps on our side of the shop. Right. Every once in a while, for example, we go from a situation where we have sort of a sequence of models that actually accomplish the tasks. Speech recognition is sort of a canonical, sort of good example for that, right? Where we went from a world where we did mostly sort of just acoustic recognition, then we sort of have language models, and then sort of, we had this pipeline of things. And then we go from there to maybe systems today that begin to be more monolithic, sort of end to end, right? I'm not sure if that's what you're getting to.
So just as a concrete example, if you have a model and then you retrain, so now it's a new model, right? How do you guarantee that it does the same things as the old model with respect to, how do you know that it's better, for example? I mean,
that's actually, I don't, in the instances that I've seen firsthand, that's actually not that difficult. I'm sure there are instances in which it is, but think of the problem, for example, of scoring search results, right? We already have to have, we've had for decades, well, not quite decades, we're not decades old, many, many years, sort of rather elaborate evaluation systems that tells us that if you make an algorithmic change to a scoring piece of code, whether that is better or worse, right? The fact that now, instead of a sort of traditional, sort of rule-based, if you will, kind of scoring system, that there are pieces of that are learned, is immaterial to the evaluation system we already had, right? Because we already had that problem beforehand. There are people that are concerned about debuggability of these things, which is actually, I think it's an interesting problem that we're trying to understand better, and I think it's a real problem, something that needs to get better at. I'll point out one thing though about technical debt. It just came to mind. I know it was not exactly what you asked, but we often talk about machine learning as this thing that will enable things that were never possible to be done before, and in some cases, or that weren't possible before. And in some cases, that is true, right? And I guess maybe the AlphaGo case might be a good case where people really didn't think that could happen at this day and age, right? The part that I actually find more exciting about machine learning is not that. It's that it actually makes software engineers more productive. So I guess I'm hitting the productivity theme quite a bit, right? There's a lot of work that goes today in complicated systems everywhere at Google, right? That are painfully creating different kinds of layers of logic to try to make something better, when the problem as a whole actually could be learned from data. And that software engineer's time is much better leveraged by creating the right modeling framework than spending its life changing 8 lines of code every week to make small adjustments to an algorithm that has inexact answers. So I think that the real bottleneck for our world today is software engineers. And I think machine learning exciting to me is precisely that. We'll be able to afford because it's going to be cheaper to do programming sort of in many other places. That's it's a bit of a hope, but that's what makes me sort of more excited about this.
Thanks a lot.
Hi, Manu Sridharan, Samsung Research. This is a great talk. I noticed, though, that you didn't mention any particular programming language. So I was wondering if you had any thoughts you could share, say, on languages that are working particularly well for these scenarios, or places where all the languages you've tried have sort of fallen over for certain tasks.
I'm a bad person to ask this question because the last programming language I fell in love was Pascal. And I learned many years ago that it's a rather futile endeavor to get infatuated with specific programming languages. Not programming languages as a field, of course. But any one programming language, it doesn't matter how much you love it, it just won't love you back, right? That's the thing to keep in mind. Now, more seriously so, for many of our backend systems, it remains the case that C++ reigns. Somewhat irrationally so in some cases, because Java is in many ways, materially on par. And there are arguments for Java being actually more amenable to higher productivity. I'll mention one thing that we still need to solve in things like Java. I mean, garbage collection, we talk about performance idiosyncrasies, right? If we don't have tail-tolerant computing, this will always be a ding on garbage collected languages, right? If it's able to give you sort of random sort of hiccups every once in a while. Sort of having said that, I have sort of personal preferences here and there, but besides that, there's not a lot. There's a lot of enthusiasm for Go. I like Go myself. I think it's a pleasurable experience to program in Go. But I think there are others at Google that probably can give you sort of better answers about this. My only answer to you is that by and large, it rarely matters as much as we think it does, the specific language you use.
Thank you.
Saman Namar Singh, MIT, great talk. I really like your definition of big data, little time. But these systems, you are going to have, everybody is going to have input output in their wearable devices. And then you're going to have your data center miles away. How are you going to cheat the speed of light to get the time down?
I don't think this is a speed of light problem. It's a great question. For most companies that want to actually deploy global services, you will have data centers within milliseconds of users, right? So the speed of light itself is not a problem. The cost of bandwidth could be a problem, right? So that's a real challenge, right? I think that, as part of sensing the real world, for example, you can imagine that some of these wearable devices, part of what they do, we do very, very good compression. That's going to help you a little bit with the bandwidth scheme. You can imagine cell phones with good convolutional front ends for cameras, right? So that you have a very summarized piece of your recognition engine being actually sent over across the wire. It's possible that they will need a third tier, right? There's some folks that have been arguing for that, right? That not necessarily, I don't think it's going to be because of latency. I think it might be because of cost of bandwidth. If you think about streaming video, for example, sort of from every user in the world to big data centers everywhere all the time, the math doesn't seem quite to work there, does it? So it may be that for the more aggressive versions of the things that I outlined here, you might need sort of a third tier. Maybe it'll be a home hub for you. Maybe it'll be in a cell tower. Maybe I think the speed of light, I'm less concerned. The cost of bandwidth, I think, is very material.
Thank you.
Vikram Adve, University of Illinois. I enjoyed the talk very much. You said a lot about productivity, or at least you said a lot about why productivity is important to you. Can you say a little bit about what productivity challenges you actually face internally and what kinds of things you think programming tools might be able to help with?
So let's see. You tell me if programming tools can help me with this. A big hit on productivity of large engineering groups at Google is you're building a system that depends on the system underneath you. And the system underneath you has a bunch of clever engineers that decide to launch version X+1 of that system. And it's almost always done in such a way that you as a client of that system actually need to do something about it. Right? This actually is very painful for people that are users of infrastructure, because this is not what they think they're paid to do. They're paid to actually innovate on top of that. And suddenly they spend a significant amount of their time churning on staying up to date with the piece of infrastructure that's underneath them. I'm sure there's a programming languages component to that. I don't think that's fundamentally only a programming languages problem. But this is top of mind for many of us today. We want to innovate faster. Part of this thing is actually create stable APIs, blah, blah, blah. But even stable APIs don't suffice, right? Because often you need to recompile the client in order to be able to sort of take advantage of something, right? If you could magically sort of make that problem go away, you improve Google engineer productivity, I'm sure by tens of percentage points, if not like a factor of 2. Thank you.